So thank you, Giacomo, for the introduction, and thank you also for the other speakers in this webinar, especially the last one, which has a huge overlap what I'm going to present today. So I'm going to talk about the control room of the future, which is part of the SUDOCO project. And today I will focus on multi-strategy wind farm flow control. So my name is Jan-Willem van Wingerden. I'm a full professor at Delft University of Technology and also coming from a control department, as also the last speaker. I also want to acknowledge that most of the slides that I will present today are made by one of my PhD students called Matteo Parigio. So let's start. So the main concept behind the SUDOCO project is to develop the control room of the future. And of course, also here, the big engine is AI. So what you see here in the blue box, is the control room of the future. And this control room of the future will take decisions based on time-varying environmental conditions and also time-varying market conditions. And then we have the ability to turn on or off some of these control technologies, such as induction control, I'll introduce in a second, wake steering, and more novel dynamic induction type of controllers. So the question is basically, when do you turn which module on or off? And of course, there's always a trade-off. Do you want to maximize power? You don't always want to maximize power. You also have the trade-off with respect to loads. And also there are other objective functions like cost of valued energy or OPEX or daily revenue. Now then you can also include other devices going to hybrid power plants, solar, hydrogen or battery storage. So in today's talk, I will focus on multi-strategy wind farm flow control, and I will particularly focus on the combination of wake steering, a well-known technique, with dynamic induction control, which is a wake mixing technology. So let's go one step back to introduce these two flow control concepts in a second. But first, I would like to again stress that typically when you do wind farm flow control, you don't have a single objective, you have multiple objectives. So today we also look at the objective of power maximization, so maximizing the yield. Please note that there's a minus sign in front of this. And there's always a trade-off. How are you going to load your turbines? How do you make sure that you also have a lifetime of at least 20 years? So in the SUDOCO project, we're also trying to develop these Pareto curves. So the trade-off between loads and yield. And later on in the project, we will do co-design, designing a wind farm in combination with advanced control to also change these lines. So going from a Pareto curve that you see here in green to the one in blue. So at the end of today's talk, you also see a Pareto curve if we talk about multi-strategy wind farm flow control. But first, let's have a look again at these flow control technologies. So I already mentioned induction control. So in the movie at the left, you see an illustration of induction control. So what is induction control? So you basically derate some of the turbines in your farm. Let's go back. You derate some of the turbines in your farm. And then you hope that the energy that you let go will be picked up by downstream turbines. Now, we have seen in field experiments and also high fidelity simulations that this technology doesn't work. At the other side, you have wake steering, which is nowadays a proven technology. And in wake steering, you try to deflect the wake away from downstream turbines. And this is now already part of a commercial product within industry. So that is wake steering. So wake steering is successful. I mean, it exists already for years. We also co-developed together with Jan-Willem the Flores model, which was already mentioned in the second presentation today. And what you nicely see with wake steering is that you deflect the wake away from downstream turbines. But you can also imagine that if you have larger farms, that still this wake is hitting other turbines in the farm. So that, please remember that statement. If we go to more advanced techniques such as the wake steering techniques, so I call them modern strategies, they are based on destroying the wake. So one of them is called dynamic induction control. So what you do is you basically make the wake bigger, smaller, bigger, smaller. So in 3D you get a pulse effect. And the idea is to destroy the wake, to get faster wake recovery. An innovation from the TU Delft is the helix. And with the helix, what we do is we basically create a helix shape in the wake, again with the goal to shorten the wake. Now, what is the effect of the dynamic induction control and the helix on a wake is again shown in the next animation. So here at the left, you see a regular wake. So this is an LES simulation, high fidelity simulation with uniform inflow. And here you see the effect of the so-called dynamic induction control, but also labeled as the pulse. So what you get is wake mixing. The downside of the pulse is that you have huge thrust variations, so also power fluctuations on the first turbine. So what is the real advantage of the helix? The helix, you get the spiral shape, the helix shape in the wake, and the power on the first turbine is constant, although it's losing a little bit compared to baseline. But the big effect of these modern techniques is that you get mixing. And if you put a turbine in the wake, as you can see over here, you get more energy out of a wind farm. So these are techniques that we already presented before the start of SUDOCO. The question that we now put on the table is, when do you want to use wake steering, and when do you want to use modern techniques such as the helix? So to summarize some of the things I just stated, some challenges with going to the next slide. So the challenges I just stated, when do you do wake mixing, right, with the helix, and when do you do wake steering? Or do you want to have a combination of the two? Do you want to have a multi-strategy? The other question, how does it really work for large wind farms? So when I go back to the case of wake steering, where we had nicely 9 turbines, you saw that wake steering was working, but you still deflect the wake away from downstream turbines, and they can still hit turbines further in the farm. The third one is, of course, this becomes a big optimization problem. So how do you solve this? Of course, the solution here is also using AI. And finally, how does it work when there is some uncertainty? Because you can have power gains of 5%, but what happens if reality is different compared to your model? So these are the 4 questions I'm going to answer in the remainder of today's presentation. So what do? We have to develop engineering models. So for engineering models, they already exist for wake steering. So you have Flores, or you have the models in PyWake. In this case, we're using PyWake. In the SUDOCO project, we developed also engineering models for the helix. So they are now part of the PyWake package, where you can now also say, okay, we would like to have the helix active. So the wake mixing strategy. And what's nice about engineering models is that you really can test them on larger wind farms. And in this case, we're going to look at the Hollandse Kust Noord wind farm, which is a relatively novel wind farm at the North Sea here in front of the coast in the Netherlands. For the optimization, we developed a new strategy based on the serial refine method developed by NWEL, but now with a multi-strategy and also generalized for different objective functions, not only for power, but you can also add other objective functions. Today we also have, for instance, the cost of actuation can be included as a measure or a surrogate for loads. So if you do this for HKN and then you optimize for helix and wake steering, then you get certain results. But you also have to take wind direction uncertainty into account. So the wind direction is always varying. It's a dynamic effect. So what we also do is we optimize under uncertainty. And yes, the amount of uncertainty is defined by the standard deviation, sigma, which can be 0, but can also be higher numbers like 2.5 and 5. And it represents the amount of wind direction uncertainty. So if we then look at the results, if we go to HKN, so this is the layout of the wind farm, and the dominant wind direction is from the bottom left of my screen. So basically from here, then you can optimize this multi-strategy approach using the tool chain I just introduced and developed within the SUDOCO project. So if you then look at the result, then you get something like this. So what do we see here? So here at the left, you see the annual energy production gain with respect to baseline. And the first 3 columns are related to single uncertainty, so no uncertainty at all. Then the black line is the multi-strategy approach, when you combine wake steering with the helix. So then you have a gain of around 2% under realistic conditions. Then the second one, let's call it the blue one, is only wake steering, and the last one is the helix. So in this case, you see that multi-strategy outperforms the other two, which I think is positive, which is a sign that multi-strategy will work. But you also see that wake steering alone outperforms the helix. But this changes a lot if you take wind speed uncertainty into account. So then you really see that the effect of wake steering drops significantly for this particular wind farm and the model that we used. And while the helix is more robust from that point of view, but you always see that multi-strategy outperforms a single objective. Now, how can this be explained? If you do wake steering, you deflect the wake away from the first downstream turbine, but it can still hit other downstream turbines. In the case of the helix, you basically make the wake shorter. So it's not really sensitive with respect to wind direction variations. And I think that's one of the big advantages of these wake mixing strategies. So if we look at more detail, and then we go again back to the control room of the future, where we can put control strategies on, off, and we can have multiple objectives. So what you now see at the left, you'll see that we turn wake steering on, and the only objective is to maximize the power of the HKN wind farm. What you see at the right-hand side is then the control strategy that you get on the turbine indicated here with the red star. So the control strategy that you get is that you do wake steering either to the left or to the right for certain directions. So that's what you see here. And for some directions, you do nothing. Right? So you get some kind of control policy on the turbine. And you get this for every turbine. If we now go for the helix, so now I turned off wake steering. I turn on the helix in our control room of the future. And then you see that on this turbine, you always, for this particular angle, where it's also the dominant wind direction, you want to put the helix on with the maximum amplitude. In this case, it's limited to 5 degrees, which is academic. I will come back to that in a second. The interesting thing is, of course, what happens if you combine the two. And there you see that for the dominant wind direction of the windrows, there you want to do the helix, and outside you want to do wake steering. Now, this is for a particular turbine in the farm. You can also do it for other turbines in the farm. So if you now pick a turbine in the middle, you get this one. So what you see in this picture is that there is a lot of control activity, right? So the controller is always active. The pitch amplitudes or you're continuously pitching or wake steering. So what you can also do is put a penalty on the amount of control effort, right? So the multi-objective aspect. And what we now basically did as an example is we looked into the control effort. So if we also put a penalty on the control effort, so multiple objectives, then you get something like this, right? So this is for a certain weighting for the control effort, but of course you can have all these kind of combinations between power and loads. And if you look at all these combinations about control effort and power, you can construct a Pareto curve, where I also started my presentation with. So if you then look at the Pareto curve, then we see multiple lines, but first let's explain this picture. So on the x-axis, you see the annual energy production gain, and on the y-axis, you see with a minus sign in front, the control effort. So if you don't have any control effort, right, then there's also no gain because the turbine is doing nothing. If you have a lot of control effort, that's basically the maximum that you can do, you end up in the kind of the solid black line, which is the combined strategy with the maximum pitch angle of 5 degrees, you get this nice Pareto curve. So the gain that you get depends also on the amount of control effort that you allow. So again, the black one is the combined strategy. The wake steering strategy is the one that you see over here. And then we have the helix strategy by itself, which is the pink reddish one. And then there are two dotted ones, and that's where we also reduce the amplitude of the helix. So instead of having 5 degrees as maximum angle, we do 2.5, which is more realistic if you look at the loads on, for instance, the pitch bearings. So still you see that the combined strategy with 2.5, so that's the black one over here, outperforms wake steering or helix by itself. So you really nicely see here the trade-off, and of course it's up to the operator to set, hey, where do I want to be on this Pareto? So to summarize, conclusions, we are working on the control room of the future and looking into trade-offs, right? So we would like to visualize these trade-offs for operators in the control room. You see that multi-strategy seems to be the optimum. And depending on the amount of uncertainty, it's more wake steering or more wake mixing. And what you also see, if you go to larger wind farms, the helix has its benefits compared to wake steering if you compare it with just the canonical cases with 1 or 2 turbines, or 2 or 3 turbines. One doesn't make sense. Because of the fact that wake steering, you deflect the wake, and with the helix, the wake becomes shorter. Then the other thing is, if you look into uncertainty, if you have a lot of uncertainty, again, then the helix or wake mixing becomes better compared to wake steering. But if there is no uncertainty, then wake steering works better. And finally, what's next? If you now can do this, right? If you can do multi-strategy control design for these type of wind farms, can we also look at co-design? Right? Can we also do a different layout of the wind farm, taking into account advanced control strategies? And are there other strategies, right? So in this case, I focused on wake steering and the helix, but you also have this pulse type of wake mixing, and there are other strategies out there. And of course, you can again also look into induction control for large wind farms. That is where I would like to stop today's presentation. But we're making steps towards the control room of the future. And I think also the future is multi-strategy. So thank you very much.